Hey everyone, welcome to the last video for section 2.5. So in this video, we're going to be talking about the difference between quantitative and qualitative analysis of these equations. Namely, what you can learn by just looking at the equation itself versus what you can learn by actually having the solution and trying to play with it from there. So let's just go ahead and start writing stuff down and we'll see where I'm going with this. So if we look at the standard logistic model for population growth, we can write out both the ODE that it satisfies and the solution to the ODE that we get from the book for solving this equation. So if we do that, this is what we get. So on the left here, we have the ODE that the logistic model satisfies, and on the right, we have the actual solution given that P of 0 equals P0. Now, if we look at the actual solution, we can see that 0 is an equilibrium point. The way we see that is if we plug in P0 equals 0, it's just always 0 forever. And you can also see that K is an equilibrium solution. If we plug in K, then the term on the bottom where it depends on T is just 0 and it's just gone. So there's no dependence on T, it's just always going to be K for that. We can also kind of look at the stability of these solutions in the sense that if we assume that P naught is not 0 or K, what's going to happen as T gets really big? Well, as T gets really big, this term here is going to go to 0. Right? If T gets really, really big, e to the minus RT is going to go to 0, which is going to cause this to, as T gets bigger, this is going to converge to just K, because I'm going to get P0K divided by P0, which just gives me K. So what that tells us is this is stable, or asymptotically stable. Be careful with that. Stable and asymptotically stable are not the same thing. This one is asymptotically stable, and this is unstable. So we can get that from the actual solution. But, like we saw in the last video, we don't actually need the solution to get that. All this information we could have gotten much, much easier from the ODE itself, right? We didn't need to solve the equation, look at long time limits and things like that. We could have gotten this directly just from the equation itself, drawing the phase line portrait that we saw in the last video. So this stuff we can get from the solution that isn't really important in terms of why we need the solution, because we could just get this from the equation as it is. The difference is, for the actual solution, we know how fast we get places. How fast do we reach certain population levels? And this is something you cannot get from the ODE itself. So let's say, for instance, if I know that I'm starting that, let's say P0 equals a tenth of my carrying capacity, just for convenience sake. How long does it take to get to 3/4 the carrying capacity? What about 99 out of 100 of the carrying capacity? See, we know that our solution is converging to K, so it's going to get past 3/4 carrying capacity. It's going to get past 99 100's carrying capacity, but we have no idea how long it's going to take to get there, just using the ODE on its own. If we have the actual solution, then we can figure it out. Then we actually have a T, we can plug in and solve for the T that gets us to a certain point, and actually know how fast we're converging to different things. So this is the main difference that I also mentioned in the first video of the course, where we can get qualitative behavior as to what's going to happen. It's going to converge to K. It's going to converge away from 0. Things like that we can get from the ODE itself. But getting the actual solution then gives us quantitative results. How long is it going to take to get there? What is the population going to be after 3 years? These are things we can determine when we have the actual solution that we can't figure out just from the ODE on its own. We would need some way to solve it to get to this information. Okay, so that's the main point here for this video, is that really both these things are important. The qualitative behavior tells you what's going to happen. The quantitative will tell you how fast. So for engineering type stuff, knowing it's going to get there is good, but if it takes 5 years to get to a steady state, it's really never in a steady state. And that's the sort of thing you need to figure out to be able to actually use it in an engineering application. All right, so I've got one problem for you to look at here, and it's going to be sort of doing this sort of how long it's going to take to get to a certain time. So we'll do that, and then we'll be done with this section. All right, So here's a problem for you guys to look at. I've picked numbers for R and K just to make it easier to deal with. What I want you to tell me is how long it's going to take, when is the first time the population reaches 70. I also want you to think about 110 as well. So think about that one a little bit. See what answer you get. If you get an answer that seems weird, maybe that's what it should be. Take a look, see what you can figure out for that. It should make sense what the answer should be. Um, so take a look at that problem, put that on the worksheet, and that's it for this section. Thanks a lot for watching, and I'll see you guys for the next section talking about exact equations.